Imagine peering into the core of matter, unveiling the secret patterns that dictate everything from the hardness of diamonds to the structure of life-giving proteins. This is not the stuff of science fiction, but the reality brought to us by X-ray crystallography. Since its inception over a century ago, this powerful technique has transcended mere scientific curiosity, becoming a cornerstone in fields as diverse as materials science, pharmacology, and even space exploration. In this essay, we explore the dynamic journey of X-ray crystallography from its serendipitous beginnings in the snowy Alps to the high-tech laboratories of today. The seeds of X-ray crystallography were planted in 1912 when Max von Laue, propelled by curiosity and theoretical insight, directed his students to pass X-rays through a crystal. This experiment defied the prevailing skepticism, revealing that crystals could indeed diffract X-rays into predictable patterns. This unexpected success not only vindicated von Laue's bold hypothesis, but also opened up a new realm of scientific inquiry. By revealing the atomic structure of crystals, this experiment laid the foundational stone for modern crystallography. Von Laue's achievement was recognized with the Nobel Prize in Physics in 1914, affirming the significance of crystallography. This accolade underscored its potential, setting the stage for decades of scientific exploration and discovery. In the narrative of crystallography, few names are as prominent as that of William Henry Bragg and his son, William Lawrence Bragg. This father-son duo further developed the technique, making it accessible and applicable to a wider range of materials. They formulated what is now known as Bragg's law, which relates the angles at which X-rays are diffracted by the crystal lattice to the lattice spacing. This law became a fundamental tool for scientists to determine crystal structures. Their pioneering work was recognized with the Nobel Prize in Physics in 1915, marking the rapid succession of significant advancements in the field. Their legacy is not just in their discoveries, but in setting a collaborative model in scientific research. The progression of X-ray crystallography is closely tied to technological evolution. From the early days using rudimentary X-ray tubes to today's highly sophisticated synchrotrons, each technological leap has expanded the horizons of what crystallographers can see and understand. The introduction of synchrotron radiation was a game-changer, providing beams of unprecedented brightness and allowing for the examination of incredibly minute details. These intense X-ray beams are essential for studying materials under real-life conditions and in real time, which is crucial for dynamic experiments. Moreover, the integration of computer technologies has revolutionized the field. Advanced software now assists in the complex calculations required to interpret diffraction patterns, enabling faster and more accurate analysis. This computational power, combined with physical advancements, continues to push the boundaries of crystallography. X-ray crystallography has been instrumental in medical science, particularly in the understanding of biomolecular structures. The most famous example is the elucidation of DNA's double helix structure, which was significantly supported by Rosalind Franklin's X-ray diffraction images. This profound discovery has paved the way for numerous advancements in genetics and biotechnology, influencing everything from forensic science to the development of gene therapies. Similarly, the structure of countless proteins has been determined through crystallography, informing drug design and providing insights into disease mechanisms. These applications highlight the critical role of crystallography in developing new medical treatments and diagnostic tools, significantly impacting public health and medicinal chemistry. The industrial applications of X-ray crystallography are vast and varied. In the materials science domain, it is used to discover and enhance the properties of metals, polymers, and composites. This is particularly important in industries where material properties are critical, such as aerospace and automotive manufacturing. For instance, in aerospace, understanding the crystal structure of components can lead to the development of more resilient materials that can withstand extreme conditions. Similarly, in the semiconductor industry, crystallography is essential for the development of more efficient and powerful electronic components. These applications not only demonstrate the versatility of crystallography, but also its importance in driving innovation and economic growth in various industrial sectors. NASA's Mars Curiosity rover is equipped with an X-ray diffractometer, a testament to the importance of crystallography in space exploration. This tool allows scientists to analyze Martian soil and rock samples, helping to uncover the planet's geologic history and assess its habitability. The implications of such analyses are profound, offering clues about the planet's past environments, which may have been conducive to life. Moreover, understanding the mineral composition of Mars and other celestial bodies can aid in future missions, potentially assisting in the identification of resources that could support human colonization. This application of crystallography not only highlights its utility in traditional laboratories on Earth, but also its adaptability and significance in extraterrestrial environments. The history of X-ray crystallography is dotted with significant milestones that have shaped its path. From the initial discovery of X-ray diffraction by crystals in 1912 to the recent advancements in synchrotron technology, each milestone has brought new insights and capabilities. Noteworthy among these is the first X-ray crystallographic analysis of a protein structure, myoglobin, in 1958. This opened the door to structural biology, a field that has since been fundamental in understanding biological processes and designing pharmaceutical agents. These milestones not only reflect the advances in understanding and technology, but also the growing implications of crystallography in various scientific fields and practical applications. Recent advances in crystallography include techniques such as cryocrystallography, which involves cooling samples to cryogenic temperatures to reduce radiation damage during X-ray exposure. This technique is particularly useful in studying biological molecules, which are often too fragile for conventional X-ray analysis. Additionally, the integration of artificial intelligence and machine learning is transforming crystallography by enabling the automation of data analysis and the prediction of molecular structures with minimal human input. These technologies not only increase the efficiency and accuracy of structural determination, but also open new avenues for research that were previously considered too complex or time-consuming. These modern techniques are setting the stage for the next era of discoveries in crystallography, promising even deeper insights into the atomic and molecular makeup of materials. X-ray crystallography is not just a tool for research, it also plays a significant role in education. Many universities around the world offer courses and programs dedicated to teaching the principles and applications of crystallography, underscoring its importance in the scientific curriculum. Beyond formal education, crystallography is also featured in public science exhibitions and outreach programs, helping to spark curiosity and inspire the next generation of scientists. These initiatives are crucial for demystifying a complex subject, making it accessible to a broader audience. The educational impact of crystallography extends from the classroom to the community, highlighting its significance not only as a scientific tool, but also as a subject of learning and fascination. As with any scientific field, crystallography faces its own set of environmental and ethical challenges. The production and disposal of crystallographic materials, energy consumption of X-ray equipment, and potential hazards associated with intense radiation sources are concerns that require careful consideration and management. Ethically, the field grapples with issues related to data sharing and the pressure to publish results quickly, which can sometimes lead to disputes over data ownership and intellectual property. These challenges underscore the need for robust ethical guidelines and sustainable practices in crystallography to ensure that its benefits are realized without compromising ethical standards or environmental health. Addressing these considerations responsibly is essential for the continued advancement and application of crystallographic techniques in a way that benefits society as a whole. Investment in crystallography research has significant economic implications. Governments and private sectors around the world allocate substantial funds to crystallographic research, recognizing its potential to drive innovation and create new technologies. The economic impact of crystallography extends beyond its direct applications in industries. The development of new materials and drugs, informed by crystallographic studies, can lead to the establishment of new companies and the expansion of markets. Moreover, collaborations between academic institutions and industries often result in the commercialization of research findings, contributing to economic growth and job creation. These aspects highlight the role of crystallography not only as a scientific endeavor, but also as an economic driver that supports a wide range of industries and sectors. Crystallography has also made its mark on culture, influencing areas as diverse as art and entertainment. The intricate beauty of crystal structures has inspired artists and designers, leading to creations that reflect the symmetry and complexity of molecular forms. In popular media, crystallography has occasionally been portrayed in the context of scientific discovery, contributing to its mystique and public fascination. Such representations can enhance public understanding and appreciation of science, although they also necessitate accurate and responsible depictions to avoid misinforming the audience. This cultural resonance of crystallography underscores its impact not just in scientific circles, but also in the broader societal context, influencing how science is perceived and appreciated by the public. Despite its many advancements, crystallography is not without its challenges and controversies. One of the major ongoing issues is the protein crystallization bottleneck, in which many proteins cannot be crystallized easily, hindering their study. This represents a significant barrier in structural biology, impacting drug development and other applications. Furthermore, the field has witnessed its share of controversies, particularly relating to credit and recognition. The most notable is perhaps the debate over the contribution of Rosalind Franklin to the discovery of the DNA structure, a controversy that highlights issues of gender bias and recognition in science. These challenges and controversies remind us that crystallography, like any other field, must continually evolve and address its internal and external criticisms to progress and maintain integrity. Looking forward, the future of X-ray crystallography appears vibrant and promising, driven by continuous technological innovations and interdisciplinary applications. Emerging technologies such as X-ray free electron lasers, XFELs, are opening new possibilities for observing atomic and molecular processes in real time, potentially revolutionizing our understanding of dynamic systems. Predictions for the next decade include advancements in automated crystallography, increased use of machine learning for pattern recognition and prediction, and perhaps a solution to the protein crystallization bottleneck. These developments will likely expand the scope and impact of crystallography, continuing its tradition of enhancing our understanding of the microscopic aspects of the material world. As crystallography marches into the future, it carries the potential not only to illuminate the structures that make up our universe, but also to shape the future of technology, medicine, and science in ways we are just beginning to imagine.